Recording officially and say happy garbage day, everyone. It's Tuesday. It's back to being cold again. Woo. Woohoo. But apparently whatever snowstorm was forecasted for tomorrow was going to miss us, so there's that. We'll get to see our dead grass instead of snow on the ground for much longer. So even though we don't have perfect attendance, you guys had a perfect record for turning in your homework 1 effort drafts. Every single person submitted something. So good work on that. I have not opened them yet. So that will be my task for tomorrow, is to open them and assign points based on effort, as promised. On Thursday, we are meeting on Zoom only. We are being kicked out of this classroom for comprehensive exams. So I decided to take advantage of that format to move that discussion of homework 1 to that day so that we're all sort of like on the same page in the same Zoom room. And because I want folks to actually participate and volunteer answers and ask questions and that kind of thing, one more person here, I am not going to record it for YouTube. I'm going to record it for our personal use for the class, and I'll share the link to the video that will be unlisted. So the public won't see it. That way you can refer back to the recording if you want to, but then you can not worry about how you sound, on the internet. Right? Clearly I don't worry about that. I'm just going to sound like I sound. It's fine. But I want to be sensitive to the fact that not everybody feels that way. So that will encourage more participation. So I hope that you come. I hope that you come prepared with your answers so that I can call on folks and have you read what you wrote, or at least summarize it, and we can talk about the high and the low points. Next up then, available to you, is your first formative assessment. Now these are worth 3 points a piece this semester, so it's a little bit more involved. And in particular, I am taking an assignment that we did last time and carving it up into pieces into formative assessments, where you are going to play correct the AI. So there's 2 actual responses from AI to questions that I asked, and I want you to read them, see what you think is accurate, and see what you think is inaccurate. Because what I have found in using that is that if you don't know what you're talking about, it sounds plausible and fine. But the more you know, the more you're like, really? So given that the use of AI is increasingly common, particularly when people don't know how to do things, like code or otherwise, I think it's good for us to all be critical consumers. In fact, I'm an author on a paper that I'm pretty sure reviewer 2 was ChatGPT, because the comments on it were so generic and just completely off base that I was like, wow, no human would have written this, and it went through. So this is our world we're now living in. But it's good for us to learn how to negotiate.
Was AI?
The review.
Okay.
Reviewer 2 was ChatGPT. I am 100% certain, based on the content of the review.
So you meant the paper was?
No. No, this is a paper that I helped with, and I would never put my name on something that I suspected where the opening paragraph is, certainly, I can help with that. No, that's been in papers. I keep seeing like memes on the internet that start with that, and I'm like, really? You couldn't even read what it gave you? Come on. But anywho, that's not us. We're going to learn things on our own so that we can not be like that. So, recapping. Thanks for doing homework 1 on time. We're talking about it on Thursday in relative private, and we're meeting on Zoom to do that, and formative assessment 1 is next. And then the next thing you'll have to do is the revision to homework 1, where you can revise your answers however you like, and then I'll read them for real. Okay? Cool. Anything I'm forgetting? No, we're good? All right, then tell me what you remember from last time. We'll look at the beach while we do that.
Like from last week?
Yeah, like Thursday. It was 5 days ago. It's been a minute.
We were talking about smushing.
Smushing with the gesture.
Yes.
Yeah, what is smushing?
If I remember correctly, it was a problem that you have with the time-varying predictors.
A problem with time-varying predictors.
That the effect is aggregate. I mean,
yeah,
smushed.
it's smushed.
I try not to use smushed in
yeah,
the
I know.
definition.
You can phone a friend if you want.
Sure, if anybody would like to help and add, but like the effective time in your time-varying predictors gets smushed and estimated incorrectly.
It's incorrect, and smushed is the word that I use. Conflated is a synonym for it that is probably more common. What is being smushed specifically, though?
Two separate slopes, either like between your contextual and the within.
So two separate slopes. So essentially the time varying part of the variable should have one relationship to the time varying part of the outcome. The time invariant part of the variable at the between level would have a logically separate relationship. So is it like being a stressed out person is bad for your health, or is it when you're relatively stressed out relative to your normal levels, you feel worse than usual? Both of those things can be true at the same time. So in general, it's an omitted variable problem where one predictor is being forced to do the work of two. So there's two slopes that it could have, and you're only giving it one. So we've been talking about ways to solve that problem, right? And we had an example that we started. So just to reorient us back a little bit here, two kinds of slopes we talked about before. So let's see. One option to solve this problem, person mean centering. This is where we literally create new variables to represent the parts of the time varying predictor. So we take at level 2 the mean across the rows from that person. We subtract some meaningful constant so that 0 means something. And then person mean x is the notation I'm using to describe this. So then if we use the sample mean, for instance, as the constant, having a high value on this means you're more than other people on this variable. A low value means less than other people on average. But than other people is the comparison point for what the variation represents. At level 1, we do a new kind of centering. Blow this up here. So we're centering at a variable, not a constant. That's the key idea. So this is called a bunch of different things depending on the context in which you are centering. In this context, because we're talking about level 1 occasions within level 2 people, we have a person mean as the centering thing. So we're subtracting a variable. We are changing the information in this time varying predictor. We are removing the people part. So when you have a 0 on this new variable, so it's your original x, quit it. There, sure. You have your original x, xti minus x bar, that's how you notate person mean, and note that's the uncentered version. Then when you're at 0, you're at your own mean. And when you're above 0 on this variable, you are higher than usual. So more than usual, less than usual at level 1, as opposed to more than other people or less than other people at level 2. That's what we've been talking about. So how does that sit with folks? Okay so far? All right. Do you remember the story we were looking at in terms of the example? Maybe? Ish? Yeah, ish, yeah. So this is a simulated data set based on a real one that I helped analyze when I was a postdoc. And it was a study of within-person fluctuation. So it's observational study, 20 consecutive days. They asked them things about like negative affect, positive affect, stress levels, how sick they felt, and most importantly, they had an indication of how well controlled their diabetes was with the glucose reading the next day. So we're looking at things that happen like on a Friday, predicting Saturday morning's glucose reading, because it takes time for these things to kick into gear. And because this was a fluctuation study, a growth curve model wouldn't make a lot of sense. Like your glucose is not going to improve or get worse systematically over the course of the study. So there's no time effect. But I also forgot to mention last time that in the original data, I went through the whole process of looking at alternative covariant structures and what should be in there. Random intercept only 1. So I was like, okay, that's the simplest case. I'll stick with that. So that's why in this example, all we have with respect to the model for the variance is just a random intercept variance at level 2, residual variance at level 1, and there's no kinds of residual correlation otherwise. But in real life, that's something that you would want to check before we start adding time varying predictors or time invariant predictors. So I have it noted here that in my code, I'm explicitly saying that the R matrix is diagonal, even though that's the default, just to remind folks that that's a thing that you should be paying attention to and thinking about. Likewise, when I'm building the variables here, we did stata last time, we'll look at R this time. I am first creating a new column in my data set for person mean negative mood, that's my predictor of glucose, and then I am centering it at 0. Now that doesn't change anything, but it's again to remind folks that this is something that you'd want to think about. Any constant that makes the fixed intercept meaningful would be a good choice. At level 1 then, I am creating a level 1 pure predictor, a within specific predictor, as original negative mood minus this new person mean negative mood that I just made. And then I also have just the original level 1 predictor uncentered, because we're going to look at models that have that version of it instead in the second half of the example. And because I'm not doing anything to address missing data, I'm making sure that my sample has complete cases with everything that's going to be part of the story, which is going to be glucose, mood, and gender. So we're looking at gender differences in this case. So now does that ring a bell? Better? Okay. So we looked at empty models last time. First for the outcome of glucose. So then we have an intraclass correlation of glucose of about 0.69. So about 70% of the variability in glucose is because some people are higher or lower all the time due to person mean differences captured by the random intercept. I then computed intercept reliability as ICC2 to give you an example of how to do that. Lights are going out outside again. And I did that in both packages, a function and R I built for that. Now I also did the same thing for negative mood as a predictor. That's not something we typically do. Like last semester, that never happened. We never did intraclass correlations for any predictors last semester. Can you guess why? Did I skip? Did I forget? Did I lie? None of the above. Zoomers, I'm watching the chat, or you can talk to us.
Is it because we had time, we were only dealing with time invariant predictors?
We only had time invariant predictors.
So we didn't need to correlate across time with the predictors.
With the predictors. So what is an intraclass correlation going to be for a time invariant level 2 person thing? We got 1 vote for 0. We know it's an extreme. The other choice is 1. Okay, we got 2 zeros and 1 vote for 1. Zoomers, what do we think? Time invariant predictors. What is their intraclass correlation going to be? I'm waiting for more people to weigh in. Okay, now we got 2 zeros, 2 ones. Oh, 1 0 went to 1. It is 1. Because the ICC is the proportion of variance that is between persons. If it's the same over time, time invariant, there is no within variation. So an ICC of 0 would be the opposite. When we had time as session of practice in our response time example that I beat to death, everybody had the same 6 sessions as their time metric. So that ICC would be 0 because there is no between person information in that time metric. The next unit we're going to do is for accelerated designs in which that is no longer the case. And we're going to borrow some of the same methodology to address that situation. But in this case, I am doing an intraclass correlation for my negative mood time varying predictor. And the question would be, why? Why is this useful to know? Drinking my water today.
Understand how much is between and within, because if you're thinking about like the residual variance and the random intercept variance, kind of understand the proportion.
Yeah, we want to know what the ICC is to know what kind of effects this predictor can have on our outcome. If the ICC is somewhere in between, we know that there is within-person variance to some extent, and that within-person variance can relate to that of an outcome. If there is between-person variance to some extent, that variance can relate to an outcome. So it's a logical prerequisite to have variance at each level before you worry about fitting an effect at each level. So last semester, when we had time, the only kind of effect it could possibly have is within persons. You're measuring within person change because time didn't vary across people. Likewise, when we had, I think it was abstract reasoning in one of the examples, that was only measured once. So it can only have a between effect. It doesn't vary within people. It doesn't have that kind of information in it. So we're finding out if we need to worry about a smushing problem, because in the vast majority of cases, we do. ICC for mood is 0.39. So 39% of the variance is because some people are grumpier than others, and the remaining is because some days are worse than others. And a likelihood ratio test tells me that that correlation of 0.39 is significantly greater than 0. Therefore, we need to worry about this. Okay, then we started in on fitting models of mood as a predictor of glucose. Log transform glucose to be specific. So the values are sort of like, I don't know what a good glucose is. I certainly don't know what is it?
100.
100. What's a good log glucose then? I have no idea, right? And I didn't need to, because I'm like the methodologist on the project. It's like, tell me what Y is and tell me what X is, and I'll just, in my notes I have it that way, and then at the end I translate it back into what the variables actually mean, because X and Y don't care, math don't care. But, so the numbers are somewhat arbitrary, but that's okay. Let's see here. So I'm making 2 new variables in the first place, and I'm now putting them into the model. So original time varying mood was centered at the person mean, and then I have the person mean centered at 0 in the level 2 model. Those 2 go in as main effects to start with, and as fixed effects only to start with. Let's look at the output. We had started with this last time, I remember. And I said, come back next week for the exciting conclusion of, is being grumpy bad for you? So my fixed intercept is 4.93. That is the expected log morning glucose for what kind of person when? Asking for you to put into context what a 0 means for my 2 predictors, because that's what my intercept refers to. Within person negative mood is the first one, and person mean negative mood centered at 0 is the second. So 4.93 is the predicted log morning glucose for, oh wait, it's cool. You can't outweight me.
Would this be for an average person at time 0, aka first thing in the morning?
Close. Average person with respect to grumpiness. So 0 is the mean for this variable, and I've used that as my centering constant. So this is someone who has person mean negative mood at an average level. And then we got with respect to time. Is time in the model? It is not. So it's not time 0, and it's not time of day per se. That's not a predictor. These were always completed in the morning. But you can say when within person negative mood is at 0, which means for an average person on an average day. Like this is, I'm at my usual level. What is my usual level? Oh, it's 0. So someone who's at 0 on that day, and who tends to be at 0 most of the time as a mean.
And did you say this was a log?
It's a log transform variable because it was hella skewed. So that's why the values are even weirder. Like I don't know what a 5 is on a log scale, but you could exponentiate it and tell me if it's anywhere near good, but not particularly relevant. So this is, to me, this is where communication is really, really important, because if you are reading a manuscript and it looks like the same variable is in there twice, right? It's negative mood. It's like, why? Is that not redundant somehow? It's not. We've carved it up into the level 1 part of mood, that is the within variable, and the between person part of mood, that's this one. So they're doing different things. So both slopes are positive. Both are significant at a conventional level. It's probably easiest to start with the second one. So for every is always the start of a slope sentence, right? For every, this is the part where ChatGPT or Copilot could help us, right? For every 1 unit change in that, which means for every unit a person is on average above their, like somebody who is 1 unit more than the average person, like for every unit you go up in person mean negative mood, your average glucose the next day goes up by 0.07. So average mean, person mean mood predicting average glucose at the between person level. So grumpier people have higher glucose on average. That's how I would say that. That's funny? I don't know.
I-
It's easier to put it into terms that are like,
My mom's a type 1 diabetic, so.
I'm not commenting on,
Yeah.
this is not causal inference class.
I had that
This
this
is-
morning.
No, this is association class. These things go together, not sure why. Maybe having to stick yourself with needles makes you grumpy.
Yeah, crazy how that works out.
That's how I would react. I'm pretty sure that would be a death sentence for me because I hate needles and there's no way I could just do that all the time.
They have
But
they have a lot of different ways to do it. Now.
yeah, there's like
It's
a
lot
thing
easier
that you
than it
live
is,
with
but
all the time, but still, nevertheless.
you still have to stick it in your.
Yeah, maybe that makes you grumpy. Who knows? So for every unit grumpier someone is than other people on average, that's the take home. Average glucose is higher by 0.07.
I'm sorry, could you say that beginning part again?
Mhm. For every unit grumpier someone is than other people on average. Than other people on average is the key. Average glucose across the 20-day period, on average, goes up by 0.07. So grumpier people have higher glucose on average. Now the next one. A within-person slope at level 1. For every unit grumpier I am than usual, than my average. I like than usual because average in the sentence like too many times gets confusing. So for every unit grumpier than usual, glucose that day. So the data set is set up so that it's like yesterday's negative mood predicting today's glucose, like since it's the next morning. So for every unit grumpier you were yesterday, today's glucose is higher by 0.01. And that's a tiny number, but these are tiny scales. So standard deviation of this variable is roughly 1. Significant though. Got a lot of sample size. So for every unit grumpier someone is than their usual, their glucose the next morning goes up by 0.01. All right, with me so far? Questions or any of that you want me to repeat? No? Good? Okay. Then let's look at some other stuff. So in the Stata output, they give you the F-test for the model already as a default thing. So R does not do that in Elmer, so I added a command to do that. Contest MD sounds like a TV show, actually, but no. It means multidimensional hypothesis test. So I am asking it to lump together the within slope and the between slope of negative mood to get a joint hypothesis test. So is mood related to glucose as a question? This is the answer. Yes, it is. How is it related? More specifically, I will report these things. And as a reminder, all of my examples that are not from my textbook have a results section, and so does this one. So at the end of this, there's a whole lot of words that is what I said. Okay, let me see what else we got up here. Make sure I'm hitting all the stuff. So effect size. How related is mood to glucose? Significantly. That's not the end of the story. I've got a couple different choices for effect sizes I can rely on. One is total R-square. That tells me how correlated the glucose predicted from the fixed effects is with the real one. So I am creating a column that is the predicted from mood, I should say, predicted glucose. Then I am quietly correlating it with the real one, meaning I don't need to see the output. Saving the answer as a variable and then printing that, because I'm going to do change in R-square against subsequent models. So the analogous code for that in R, I built a little function for it to do the same thing. Yay me. Still proud of myself. And it wants to know your data set, the name of your outcome, the model object, and then a name for the label. So then it goes behind the scenes and does everything else for you. So the total R-square is 0.02. Woohoo! So 2% of the variance in glucose is related to mood. It's not a compelling effect, but it is significant. The other way to think about this is pseudo R-square. So each of the variances that we have, we can see how much of it was explained, and I'm computing it the easy way. So this is what it was minus what it is over what it was. So taking the variance components from the empty model as my baseline, using the ones from this model as the alternative model, and then computing the proportion change in each. To do that in Stata is a little more involved. It's this right here. So what's happening is I've saved this object and then found where the variances were that I needed from the object. So I have the object from the empty model, and I have the object from this one, and then I had to turn them into variances instead of log standard deviations. So this will end up showing the same numbers that we get out of here. Now the question for you, which kind of variance was explained by which kind of fixed slope? We've got intercept at level 2, that's between people. We've got residual at level 1, that's within people. So we'll start with the first one. Which one got me lower random intercept variance? The level 1 predictor within person negative mood, or the level 2 predictor of person mean negative mood? Got 1 vote for 2, 2 votes for 2. Yeah, I kind of gave it away in the way I worded the question, but that was sort of deliberate, because it is that straightforward. Like, it's a between person thing. It explains person mean differences in glucose. So mean differences in mood explain mean differences in glucose over time. That means level 1, the time varying residual part, is explained by time varying negative mood, the within part. Being grumpier than usual relates to being more glucosey than usual. Sicker? I don't know how to think about what a relatively high glucose is. I don't.
I like
Glucosier.
glucosier. That is fun.
Yeah, I'm gonna go with that.
Let's make that a mouth.
Yeah, I think so. So in this case, there's only 2 variance components. It's relatively straightforward. As you might imagine, it gets uglier very quickly. All right, questions. Now there's one piece of output here that I've been skipping over very conveniently. In each of these packages, I have done lincom statements, 2 of which are redundant with the output and 1 that is new. I'm going to introduce these concepts in just a minute, but we're not there yet. So I'm going to keep skipping over them from now with your blessing. All right. Next up, so far we are assuming that the effect of within-person negative mood is the same for everybody. That 0.01 more grumpy than usual translates into, or 1 unit grumpier than usual translates into 0.01 more and glucosier. But do you think that the relationship between mood and glucose might differ across people? It seems so. Can you think of like a way we could ask that question? Random slope, yeah. So we had random slopes last semester, right? Everybody gets their own. They got their own effective time last semester. They're going to get their own effect of mood this semester. The concept has not changed. How we implement it has not changed. How we evaluate it has not changed. So I've added what to my equation that allows me to have a random slope? We'll play Where's Waldo?
What was it? It's the ID after the, or, yeah, is it the ID?
ID? Here. I'll make it big. Level 2 predictor. Now we had one that, oh, that might be an old answer. Yeah, that's from 3 minutes ago. Sorry. What's new? Yeah, this person right here, UI. So we've added to the within-person mood equation for beta 1. We had our fixed effect, now we have our random effect. and it's 1i because we're predicting beta 1. And there's no time slope in the model. Wasn't needed in the data, and I wanted to just focus on the new parts. So we add it in terms of the code to Stata, changing 2 things. Stata users, this question is for you. What 2 things did I have to change to get a random slope in my model?
You have to add within person negative mood.
Yep, the variable the slope is for gives it a variance.
Yes.
Yep.
And then you have to add the covariance.
Yeah, this thing right here, that's new. I, in my textbook examples on the website, I leave that in for every model because I don't want to have to remember to turn it on and off, and I've had people be like, oh, that's not necessary. Like, I know. If you only have one thing, a covariance of the one thing doesn't really make sense. But what I'm doing is creating an unstructured G matrix. So G matrix is where the random effect variances and covariances live. That will always be unstructured. Nothing else makes sense. The default is to omit the covariance between the 2 random effects. So the slope and intercept from the same person have nothing to do with each other. It's not reasonable. So this changes it to be all possible covariances among the random effects estimated separately, as well as allowing the intercept variance to differ from the slope variance, which is also the only thing that would be reasonable. It would be very special cases of like trying to trick this into something it wasn't meant to do where you would change that, but not in this kind of standard use case. So residuals independent, that refers still to the R matrix. So the 20 days, like if you picture a 20 by 20 matrix, that thing has just a diagonal of residual variance that's held constant over days and zeros everywhere else, saying that the random intercept and slope now are enough to model the correlation across occasions from the same person. That's empirically testable, but that's what we got. In R, skipping this for a second so I can get to the thing here. Stata output this time. Where'd it go? Lost it. There we go. In R, I added my within person negative mood to the inside parentheses that denote random effects, and it automatically estimates correlations between them. I don't actually know how to shut that off if I needed to. I'd have to learn that. I've never needed to. To my earlier point, that's how it should go. The Snyders and Bosker textbook, I don't know if you've looked at that. It has 2 different editions, and in each edition, when they talk about random slopes, they have a subsection header that says, don't force the covariance to be 0, exclamation point. Like that is the title of that section. So, okay, you got it. Yes, sirs. All right, so what happened? This looks pretty much the same, except I've highlighted 2 things in here that are relatively different. So I had degrees of freedom now, after adding a random slope of 192, that's relatively close to the number of people, and a standard error for my within effect of 0.004. In the previous model, my within person effect standard error was 0.003, and degrees of freedom were like 4,000. So this is expected. When you're using Satterthwaite degrees of freedom, a level 1 predictor that does not have a random slope is treated as a level 1 thing. Once you add a random slope, it becomes a level 2 thing. So it's going to have a higher standard error because the slope variance will bump that up, and it's going to have fewer degrees of freedom because they should be based on people and not days. So it is entirely possible because of those changes that if you add a random slope, the fixed slope becomes non-significant. Would we chuck it or keep it?
Did you say check it?
Chuck, as in remove. In that case, like if we add the random slope and the fixed slope that goes with it becomes non-significant, hypothetically, do we remove it or do we keep it? We keep it. Because, as shown here, the random slope is a deviation from the fixed slope. If we remove the fixed slope, we're saying it's exactly 0, and that's not the case. It's just significantly not different than 0. So we leave it in. It serves as the average slope for the within person slopes in that case. So those 2 results change, but the coefficients are pretty much the same. It is the average within person slope now is how we would think about that. Let's see. We have a new slope variance of 0.0005. That's pretty small. But look, I have a chi-square of 4,000. Doesn't that mean it's significant? Nope. What's my clue that that is not what this is talking about? The 3. Yeah, what's the 3 refer to? Degrees of freedom. So this 4,000 chi-square statistic is removing all 3 of my level 2 terms from the model for the variance at the same time. That's why it's 4,000. Because there's a whole lot of intercept variance. What we want to focus on is this one and this one, because that's new relative to what we had before. How do I do that? 3-word phrase, first word starts with an L. Very close. It's either a log likelihood difference or a likelihood ratio test. Yeah, if you're in likelihoods, then you're dividing one by the other, but no software prints likelihoods. They only print log likelihoods. So then division turns into subtraction. In reverse, if you're multiplying things in likelihoods, you would be adding them in log likelihoods. So that's why the log likelihood is literally the sum over people of the individual log likelihoods. And that's how we know which parameters make the data the tallest. So yes, likelihood ratio test for that one. Also printed the G correlation matrix to see what the correlation between the intercepts and slopes was. Want to make sure that that doesn't go out of bounds or try to go out of bounds. Then I'm using the LR test command, where the model with more parameters comes first, the model with fewer comes next. Survey says chi2. So that's our clue that it's getting it right. And our test statistic is 3 with a p-value of 0.2. So then my question, what does this result mean? Is this a better model than the one we had before? No. Nope, I would agree. So I would say this means our model adding a random slope variance and then the covariance between the slope and intercept is not better. That's how I would say. When you add things, it's better or not better. When you take things away, it's worse or not worse. So we didn't help. But that's not the end of my sentence. Model fit was not improved. Comma, indicating that, what's the end of my sentence? Sentence. Making up gestures. Indicating that, or such that, or other transition late word. Conceptually, what does this result mean? I don't need the random slope, which means it's not varying, not within a person, between people. Yes, the slope itself is capturing a within person effect. The variance is across people, though, in it. So it's between person variance in a within person slope. Or people change the same. I would say people change due to being grumpy the same, because change is a time word. The effect of being grumpier than usual is roughly the same for everybody. That's what I would say.
Okay, so model fit was not improved, indicating that the between person variant.
That the effect of mood within persons is roughly the same across people.
Got it, okay.
Yeah, people don't need their own slopes. The shared one is good enough. That's the key idea. Now, Stata has this as chi2 instead of chi-bar, meaning they're using a chi-square distribution with 2 degrees of freedom as the reference distribution by which to compute this p-value. What if reviewer 2 is like, hey, this should have been a mixture p-value? What do I say? No idea?
I don't remember if 2 or 1 is more conservative.
Yeah, it actually should be 1.5. So what they're talking about as indicated in the text box that I put here for myself to remind myself to make this point. See, you thought the words were for you, but they're actually for me. So the idea is that a covariance is unbounded, relatively speaking. Like a zero null hypothesis as the center of a distribution makes sense for covariance. So we know we get one. But the other, for the variance, the zero that is the null hypothesis is on the boundary. So in that case, a two-sided symmetric sampling distribution doesn't make any sense. So essentially what you're doing is saying, I'll use 2 degrees of freedom for the situation in which the slope variance was positive, but then stay at 1 for the situation in which it would have gone negative, and that can't happen. Like the software won't let that happen. Some packages allow you to override that default, but not all of them. Practically speaking, though, what that does is change the criterion for significance at 0.05 from 5.99 to 5.14. Either way, I'm not there. So my response to reviewer 2 would be like, you're right, but I didn't want to spend a whole paragraph explaining this when it didn't matter for my conclusion. That's what I would have said. Thank you for your astute observation that we used the wrong p-value. However, the right one still has the same interpretation. We appreciate your careful read of our results section. Yes, that is how you write a letter. Like compliment sandwich, have you heard that expression? Like, thank you, you're wrong, thank you. All right, but nevertheless, what if let's say reviewer 3 is like, I don't think you should focus on significance test. I think you should focus on effect size. Okay, fair. Let me do some stuff to focus on that. So I'm showing the results from this model and highlighting the numbers I'm going to need in the computations. I'm going to do 2 things to convey some kind of effect size. One is compute a random effect confidence interval. So I have taken the fixed slope for within person negative mood, which is this number right here, as the center of the interval. And then 1.96 for the conventional level of 0.95 times the standard deviation. So in this formula, it's the square root of the variance that goes in here, because what you're essentially doing is computing 2 standard deviations around your fixed effect on either side to describe where 95% of your sample would be expected to fall. So on average, the slope is 0.01, and 95% of my sample would be somewhere between negative 0.03 and 0.05. So seems like maybe a lot of variation, but not a whole lot. It's hard to tell with the scale of things. So the other thing I computed is random slope reliability. And again, doing this directly out of the variance components from the model. So we have, this is slope variance divided by slope variance plus the, let's see, what is this for? Yeah, residual variance. See, here's my comment, here's the formula. And then that divided by level 1 sample size, which is 20, and then the variance of the predictor, the slope is 4, which I just got here and saved. And so the slope reliability it computed is 0.15. So the way I would think about that is kind of in intra-class correlation terms, not really in reliability terms. What I would say is that of all the variation that's over time in glucose, like 15% of it is related to different slopes for negative mood. Like that's not a lot. It's not significant. So if I had a smaller sample in which rejecting a slope variance might be a type 2 error, I would be much more concerned about this. But I've got a sample of like 200 people. I should have found it if it were there. Not a lot of signal there. So it doesn't look like I need a random slope. And then our folks, I have most of the results in just Stata, but I did want to show one thing, how to figure out where the stuff is. So after I fit this model, I ran a command of varchor with it and then put it in a data frame. And then what the result of that is this little table right here. So then I can find the variances and make it do math on them. So this number is row 2, column 4. The fixed effects table I also printed earlier for reference. Saw that this was stored in the second spot. and then I have the random variance for this one as well. So I have a function then that computes 95% confidence intervals based on this input, and then a function that does random slope reliability using the same formula. So the only trick is trying to figure out where you can find the numbers to plug into the function, because it wants numbers, not places. So same output in both programs, making me feel good that the formula worked. Okay, how we doing? Thumb check? Okay so far? Okay-ish? Now, one of the things that the original investigators in this study wanted to investigate was gender differences in these effects. So I went ahead and did that. So I'm adding moderation in 3 different ways. Number 1 is a main effect of gender. So are there gender differences in average glucose? Could be, might be a biological thing, I don't know. And then are there gender differences in the between person effect? And are there gender differences in the within person effect? So the equation grew considerably. We still have mood at level 1, person mean centered. We still have mood at level 2, constant centered. Now I've added a gamma O2, and the variable I'm calling woman, which means men are the 0 and women are the 1. And then we have an interaction term. So person mean mood by gender is how I ask if being a grumpy person relates to glucose differently for men and women. And so this is gamma O3 because this is the 3rd slope predicting the intercept. Now I did something odd, but to me it makes sense. But I haven't seen this often. I deliberately omitted gamma 1,1 and I put in gamma 1,2 because then I know that the second predictor is always the same. I left room for potential what would be a cross-level interaction of person mean mood with within person mood. That's not in this story. It will be in the next unit though. And so I left room for it in my notation scheme. And I also spaced it over to kind of make that point. So I don't have a random slope here because we just found out we really didn't need it. So how then would I describe the effect of within person mood, given that it doesn't have a random slope, but it has a moderator? There's a new vocabulary word towards the end of last semester. Systematically varying, that one. So the idea is not that everybody needs their own within person mood slope, but that men might meet a different one than women. That's the idea. Had I needed a random slope and omitted it, that test would be wrong. P-value would be way too optimistic because the variance would not be adequately represented in the standard error for it.
So, kind of what we're capturing with that part, just to kind of put it into some different words.
Please.
We don't need a random slope because not everybody needs their own, but different groups within our sample need their own.
Yes. It's
We
not.
need different.
Yes. Need different ones. Yes.
Okay.
So we don't have a random slope because not everybody needs their own, but different groups in our sample each need their own slope.
Perfect.
Yes. So the slope is constant within men, constant within women, and then each group gets a different one. That's what this would imply. And I feel like that's a reasonable thing to expect. Maybe there isn't a lot of variability, but there's some that's captured by the information that we do have. Question, could you have a random slope and the woman slope? Yes. So if that were true, if we had a U1 here, along with our moderator, we would say that there are differences within men and within women that we don't know why they're there. That's the random part. But we would have to focus within groups because we already have a group difference implemented via the cross-level interaction of 1, 2 here. Cross-level. Okay. Other questions or things I can repeat? All right. So in the model, here are my 3 new fixed effects. I've removed the random slope and the covariance notation since that's irrelevant at this point. Saving stuff as usual. Got a bunch of lin-coms here that we're not going to do yet. And I made some pictures and stuff. Computed some effect sizes. But let's talk about the model first. So here's our output to do the same thing. So I've got my 3 new fixed effects here at the end. Back to a random intercept as well. Okay, zooming on in here. Now, who is the intercept for? But previously it was average person on an average grumpy day. Who's a dude? Yes, you got to add that one. As opposed to a chick. Likewise, these were my mood slopes before, right? They're still my mood slopes in dudes because of the interaction terms. These are specific to gender equals 0, which is for the men. So I've called this MW for which one comes first. That's the 0, then the 1. That's my way of remembering who the reference group is. So in men, these effects are actually quite stronger. Before they were like 0.01 and 0.07, something like that. Now they're up to 0.03 and 0.18. So in men, having 1 unit more average grumpiness than other men means you have 0.18 more average glucose. You're glucosier by 0.18. In men, if you have a worse day by 1, your glucose the next morning goes up by 0.03. Okay, good so far? Now the gender effect. It looks like women have lower glucose. The end? No, that's too simple, right? You knew that was coming. Like at the average of these variables, this is the gender difference. So the interactions imply that the gender difference would be changing at higher levels of grumpy and lower levels of grumpy. So this one is actually non-significant. But the 2 interaction terms are significant. Of course they are. I made the data that way. So then how would I talk about the within person by gender interaction here? What's it doing? Within person effect of negative mood in men is 0.03. The interaction of within person negative mood with gender is minus 0.03. Got to vote for less positive? Which is less positive? There's 2 variables in the story. If I go with this scheme of gender as a moderator, then it is the within person effect of negative mood that becomes less positive in women and actually kicks it over into negative just a tiny little bit. How about the other one? .18 is the effect of person mean negative mood in men. The interaction term with gender is negative 0.17-ish. Same thing, same pattern. So are these negative mood effects stronger or weaker in women? Yeah, what does less positive mean? Your readers are not going to like less positive, I'm telling you that. Gotten a lot of pushback from people, like, what?
Is it just like weaker? So, like if you are less, or if you are more grumpy than normal, it has less of an effect on your glucose
Exactly right.
on the averages for the within too.
Yep, exactly right. Less anything means a weaker effect. And so I started out with 4 kinds of interactions. I'm down to 2, I've decided. In intermediate, I changed my mind this year. Interaction patterns are either stronger or weaker. If the signs match, it's stronger. If the signs don't match, it's weaker. The end. That's all you got to know. And then you got to talk about it in terms of what you just said. I like that women are less affected by negative mood when it comes to their glucose. That's sounding a little causal, but we'll allow it. There's less of a relationship between negative mood and glucose in women. Weaker. Now, do I know if there is still a relationship in women? Is there anything on this page that tells me that? Now, I can get my calculator out and I can figure out what the slope would have been, but getting my calculator out for the standard error would be a lot more work. So we're going to make the software do it. So first thing I did, get a joint F-test of the 3 new gender terms. Is gender a significant moderator? Survey says yes. And then, because in practice, I do this in my own work and I do this in class, flipping back and forth through multiple sections of output to get all the possible effects is more work. It is less work to do a slightly more typing. Plus, when you come back to this model like 3 years from now and you're like, what does this mean? Because it makes sense now, but like even your own stuff you will be completely unfamiliar with sometimes when you come back to it. Future you will appreciate you spelling it out for yourself. So the labels are like the interpretations of these things. And they create a table that you can send to somebody and have them make sense of it without even needing to know what your variables are called. So I have asked for everything that I might want to know. What is the predicted intercept for men, women, and what's the difference? So this would be the main effect of gender, is the bottom one here. What was the within person mood effect for men? That was given directly by the model. What was the within person effect for women? I get that from the men one, plus the corresponding interaction term. And then the difference in those within person effects is just the interaction term. Likewise, same deal for between. The between slope for negative mood for men was given directly. The one for women is the men one plus the interaction for how it differs in women. And then the difference in the between effects is the interaction term.
And is this the same as the LINCOM?
This is exactly the same thing as the LINCOM, yep. So if I go back up to that, the Stata code is a little bit easier because you only have to type the things that you want. So I'm deliberately adding in the times ones so that the code matches across packages, but you don't have to type that obviously. And anything that is times 0 does not need to be written. But my practice is to write everything that could need to change to remind myself to change it when I need to. So those are the only things that would be relevant in building an intercept. So that's the only things that I included. But like here, I knew that for the within person stuff, I would have to include at least 2 things. So I left that in there. And comma small, by the way, is use the same denominator degrees of freedom method that you used in the model. It doesn't default to that, crazy as it sounds. Do you want to see a picture? I made one. Let's see where it is. Ah, there we go. I made a picture. I made it in Excel, though. So this is a different kind of picture than you've seen. The x-axis is not time. The x-axis is within person negative mood, and I built it as plus or minus 1, I think, because that was the standard deviation of the original variable. But I have simplified that labeling structure to say lower than usual, usual, or higher than usual. So that means that the slopes that we're seeing through the x-axis are those the within effects, the between effects, or neither? The slope of these lines, are they showing the within negative mood effects, the between ones, or neither?
They'll be within.
2 votes for within. No one else wants to vote? That's what I'm waiting for. 3 votes for within. Yep, that's what the axis is called, so stands to reason. Yep. So these are barely not flat in men, and they're pretty much flat in women. So I have men are blue, women are red in this case. So the slope of the lines is conveying the within effects being differently sloped in men and women. And I also wanted to show the between effect. So I did that by making different kinds of people, and yes, I labeled them happy and grumpy, like the dwarves. And these are roughly plus or minus 1 standard deviation as well. You can pick whatever is convenient. And the way that I would explain this is that the difference between happy and grumpy dudes is a lot bigger than the difference between happy and grumpy chicks. Say that again. The difference between happy and grumpy dudes is a lot bigger than the difference between happy and grumpy chicks.
In regards to how glucosey they are.
Yeah. In regards to their glucositude. Yeah. Totes. It's fine. Now this picture has some parallelness to it, right? Like the blue lines are parallel and the red lines are parallel. Coincidence or consequence?
Consequence, because we got
Consequence.
rid of, that everybody gets their own slope.
I would say consequence is correct, but it's not because it's random. No, or not because it's not random, I would say. These pictures generally only illustrate the fixed effects. You could draw individual trajectories if you wanted to. That seems to be less useful in conveying interaction patterns like this. But it is a consequence of a fixed effect that's not in the model. Actually, two. We go back up to the equation and see where the holes are. Something not here and something not here. So if I wanted to say that the effect of being grumpier than usual depends on how grumpy you tend to be. The effect of being grumpier than usual depends on how grumpy you tend to be. That would be this one, gamma 1, 1, a cross-level interaction of the two halves of mood. Maybe if you're not that grumpy, being worse than usual has more of an effect on your glucositude than if you're someone who tends to be grumpy all the time. Could work. And then there could be gender differences in the extent to which your effect of being grumpier than usual depends on how grumpy you are. That would be gamma 1, 3, person mean mood times woman here, which then becomes a three-way interaction. It could be a thing. So I could have made this a lot worse, my point. Being nice again. So in terms of explained variances, let's do that part. Total R square went from 0.02 up to 0.056, so a net change of about 4%. So adding gender explained more variance. Pseudo R square. So there are 3 new effects in the model. We got to figure out which ones are responsible for the changes in these pseudo R squares. So first up, the intercept. It is now explained about 6% up from about 2%. Which term or terms did that? Your choices are main effect of gender, gender by between, or gender by within. Talking about random intercept variance explained at level 2. The first 2? Main effect of gender for sure, right? Because that's a level 2 predictor that explains people variance, random intercept variance. Also between by gender, because between is between. Yep. So level 2 interaction is what I would call the latter, gender by between person negative mood. Those are both people variables that are interacting at level 2. They predict the random intercept. And we knew that if we look at the equation, the rule is if there's a U in your line, all the stuff before it predicts it. So we add mood, person mean mood here is the between person effective mood. We added these 2 things. They should explain this U0 variance in its line. U0 is like the residual of how each person gets their own intercept. But then, now what? My within person effective mood doesn't have a U. So what's this interaction term going to explain? 1 vote for E. Yeah, that's all that's left. A couple votes for E. Yeah, so this cross-level interaction is a systematically varying effect of within-person mood reduces E. Why are you off your line today? Because you gave me the dude's line and I want my own. I'm in the other group. So within-person negative mood by gender explained. Tiny bit, a little bit more. So a change of less than 1%, but significant. All right, what did I skip? I'm just like scroll happy today. All right, Stata folks, I showed all this so you can see how I've made things, but Stata is so much faster for plots, oh my goodness. So I have Stata plots that I made with this in your download packet. So I have margins at, and I listed 3 values in this case, 2 values for between, 2 values for gender. V-squish means remove empty spaces in the lines, like condense the output, and then margins plot, where you tell it which dimension you want to be X, and then you can save it and export it. So the plot that I made in Excel could very easily be made in Stata using margins. Very cool. And then we have pseudo R-square and total R-square computed in the usual ways. Ugly, but not too terrible. The hardest thing is to figure out where the number is in the chart and make sure you've got the right one from the right model. So if you're wrong, I guarantee that's what you're wrong about, because like I take these and just copy the whole thing and then just change those pieces. So, all right, I think I did all the things. Did I do? I think I did. Oh yeah, so in the link comps here, or these versions in R, which of these things are redundant? Which of these things were actually necessary? One's with a 1, 1. Yep. If a line has 1 in one place only, it's in the model. And I didn't need to write it out, but this was for future me and future you, as it were. So anything that has to do with men is already in the model because they're my reference group. So anything having to do with women is not already in the model. Anything having to do with a women difference is in the model because that's the interaction term. But what we haven't talked about yet, and what we'll get to on Thursday, are these monstrosities, contextual effects. Yeah, and they're like, oh, look at all those negative signs. That's freaky. Yeah. I will tell you very simply what a contextual effect is. You get some output here to look at with. Here we go. So the coefficient before we added gender for the within level effect was 0.01. The coefficient for the between level effect before we added gender was 0.07. Do those numbers look different to you? To answer that, I'd probably say, well, can I see the standard errors and see like how wiggly they are? Yeah, I think they kind of look different. And lo and behold, I'm going to ask it to, actually not in that model. Let's go back to the fixed effects. One more back. I'm going to ask for it to be tested. This new term right here, a contextual effect. There are 2 ways to understand it. The simplest way is it's the difference of the within effect and the between effect. It's computed as between minus within. This is my empirical evidence that smushing is wrong. A smushed effect says the between effect is the same as the within effect. If that were true, the test of their difference would be non-significant and close to 0. But it is significant and it's not 0, which means they're different and they should stay different. It has another interpretation that is less useful in longitudinal data that we'll talk about on Thursday. All right, questions or any that you want to hear again or differently? We're good? We're full? Heads are full? Yep, I know those looks like stop talking, I'm full. Yes. Unrelated question, can you explain the mixture p-value again? Yes, I can. I will do it differently though. I'm going back to last semester. Lecture 5. This is a very long one. It's loading. Oh my, I scrolled right to it. What? Dude. That's some, maybe it heard me. Oh, that's some freaky stuff. Okay.
Copilot actually helps.
I don't know. I like it in R, I gotta tell you that. That helps save code. This is the problem. So this is a standard chi-square distribution where the critical value for 1 degree of freedom is right here, and for 2 degrees of freedom is the blue line right here. And then people were like, nuh-uh, and there's a paper about this that was on the reading list, and they pointed out this problem that you should be using a mixture of degrees of freedom 1 and 2 when adding a random slope, because the 1 is for the instances in which the random slope would have gone negative, but it couldn't. And the 2 is for when it stayed positive and the covariance can be negative or positive either way. But the difference in practice as to what these distributions look like for the normal mixture is the solid lines and the normal one is the dotted lines. Can you see this difference? I gotta zoom way the heck in to see the difference. But that's the difference. So I decided when I was writing my book that I just can't care about this. I just can't. I'm sorry. I tried and I can't. So in the textbook, that's why I have tilde 2 as degrees of freedom, meaning 2-ish, it's fine. Only when your critical value, your chi-square value is between these two numbers would it change your conclusion. So there's very few instances. The same is true in adding one random variance that could only be positive. The cutoff is 2.7 versus 3.8. So only in between these two. So other question, can you tell, hang on. Can you please explain whether I can tell if the lines in the graph are different? Like, do men have higher, okay, yes. In my graph, you would not want to do that because I put them at like plus or minus 1. But if you wanted to, like if you're plotting them for each group, then that's where you would do the contest 1D to test like the simple slope at that level of the moderator specifically. And if you had questions about continuous variables that you wanted to serve as moderators, you could write contest 1D or Lincom statements to test the slopes at those specific values. So if I wanted to, I could. I just don't think it would be that useful in the case of grumpiness because I picked arbitrary values of grumpy. Okay, does that help? Cool. All right. All right, 1:46. I kept you 1 minute late, but thanks for the questions. Well, we always start like 5 minutes late, so I feel like it's a good trade. Thanks for being here. Zoom only on Thursday. Come ready to talk, okay? It'll be a semi-private forum. All right, see you then. Let me know if you need anything. Bye for now.